Kia ora koutou. Hello and welcome all to our June WMISA seminar. I'm Lorna Strachan, based at the University of Auckland, and I'm a member of the WMISA committee. This year, I'm organising our seminar series. As WMISA is an international organisation, we wish to acknowledge Maori as tangata whenua and Te Tiriti o Waitangi partners in Aotearoa, New Zealand. We also acknowledge the traditional custodians of country and their connections to land, sea, and community. We pay our respects to their elders, past, present, and emerging. Indigenous peoples were the first Australian and New Zealand earth and environmental scientists, and we have a lot to learn from their deep knowledge that spans tens of thousands of years. The WMISA seminar series is about showcasing the amazing work of women in earth and environmental science in Australasia. All the recordings of past seminars are available on our website. You can sign up as a member of WMISA to get a notification of upcoming seminars, or you can follow us on Twitter. I'm delighted to introduce our June speaker, Dr. Coralie Siegel. Coralie received a PhD from Queensland University of Technology in 2015, where she studied the igneous processes behind uranium, thorium, and potassium enrichment in granitic rocks in Queensland. Coralie then joined CSIRO in Perth in 2017 as a research scientist. Her research focuses on the behavior of metals in both magmatic and hydrothermal systems, and utilizing this knowledge to constrain mineralization targets. She has worked on a variety of commodities, including battery and critical elements and metals that are most needed for the green energy transition. So now it's my pleasure to hand you over to Coralie.
Thank you, Lorna. So today I'm dialing in from Perth, West Australia. I'm living south of the Canning River. So this is a ford of the Canning River I took last week as I was riding back home from work with my daughter. And I live to the south of the Canning River on the land of the Bilye people. This is a clan of the Whadjuk people from the Nyungan Nation. And the Canning River here separates two clans of the Whadjuk people, the Bilye people to the south, where I am dialing from, and to the north, the Bulu people. Not sure if you can see. I might put my laser pointer. So the Canning River in Nyungan language is called the Jalgaro Bilye, and this is a place where Aboriginal and the traditional custodian used to live near the swamps. And there is a record of a camping that has been now built over, where they have found stone chips that have been dated at about 5,000 years. But there are other areas, maybe a bit further along towards Fremantle, where this, the dates on are much older, about 35,000 years. So they have been a long time in this area. And like Lorna, I'd like to pay my respect and acknowledge them, the traditional owners of the land, past, present, and emerging, and the contribution that they have done in to this beautiful country. This is going to be different. To be a bit less about science and a bit more about career pathways using a Japanese concept called ikigai. So I'd like to get started by asking you to remember what you wanted to be when you grew up. Do you remember what was your job? What you wanted to be? Did you want to be an astronaut, a baker, a mechanician, a banker, a scientist, perhaps a geologist? Feel free to put it in the chat if you want to share it. Personally, every school year I was asked at the beginning of the year what I wanted to be. So on a piece of paper, I had to write my dad's job title, my mom's job title, and what will be potentially my future job title. And I remember writing, I've never written geologist. I've written that I wanted to be a meteorologist. And once I've written that I wanted to be a surgeon. I'm not sure where that came from. But very early on, we get asked to project ourselves into our society and what we would like to be. And for some people, it's quite straightforward. For others, it's not quite that straightforward. And we often get faced at some point in our life in, oh, which career path am I going to take? So here is a bit of a schematic diagram, and it looks like it's done by a kid, but it's purely mine. So I've made an attempt to try and illustrate what career pathway means to me. So I'll start with the career pathway on the left here. So this is a career where you might start, and it's quite straightforward, and it's quite a long road, and then eventually you arrive to the edge of a river. And you kind of wonder how you're going to get across the other side of the river. Are you going to backtrack and take a different path? Or are you going to build a bridge, upscale yourself and find a way to cross that river without getting wet? I mean, there might be crocodile, who knows what's in that river. It might be very deep, it might be a very strong current. You might not have a swimway to cross it. So really, how are you going to pass that is quite a big obstacle. You might have another career path, which is more of a scenic route, and it's probably more like a traditional career path where we set ourselves a goal and we do everything in our way to get there. And it might not be quite straightforward because there might be a little bit of detour. But sometimes you might decide at some point that you don't want to do that, and you see another path that seems very interesting. You got a small bridge and you get to cross that river here and join a different career pathway. Or you might choose a career path that knows that is going to open many doors, so that if you're not completely sure, you might decide on one pathway and then, oh, well, maybe I'll change to this one. So you kind of open your opportunities there. That fourth career path here I've drawn is a way of saying, well, we know it's quite straightforward. I want to do this, but eventually you might decide, I don't want to do this anymore, and you might translate your skills to be able to move back into another career path. And the last trajectory is full of obstacles and detour, and it might be that you had to do some exams or some things that were very difficult, or some life event happened, and you have to jump several obstacles. And you might have a detour. You might stop for a year or two, do something else, raise your kids, or go on sabbatical, and then coming back to your career path. So I challenge you to try and draw and imagine what your career pathway might be like, or even get people around you to think about that. But sometimes our career path gets a little bit shaped by our school systems, or by our parents, or by our friends. So sometimes we don't necessarily get to decide. We get told, oh, you're going to do that. Or sometimes we have an idea, but people around us think that it's not realistic. I mean, you want to be a singer, it's great, but it's not going to bring you revenue. So sometimes very early on, our dreams get crushed. Sometimes we might find something that is similar and maybe a bit more realistic. So it's not a very straightforward decision, at least not for everyone. Oh, I see there are some items in the chat. Archaeologist, artist, nurse, chef, and reporter. That's awesome. Are you, any of you, still in this position today? Are you, Erin, are you a nurse or a chef? No. So something may have changed that made you, no, never became one, but maybe it became a hobby. Artist, Emily, you're an artist, or do you do it as a hobby? Awesome. I'd love to hear what sort of artist art you're doing. And archaeology, Erin, are you doing a bit of archaeology in your current science? science outreach. Awesome. Thank you so much for sharing all that. So the reason I'm looking at those different career pathway as well is because we realize that in Australia, there is, and sorry, I haven't looked at the New Zealand statistics, but in Australia, 55% of the employed population have been in their current position for less than 5 years. So there's a very, very strong mobility. And that's reflected in the current media and different institutions. So there are one in 5 scientists that have been surveyed in 2020 that have thought about leaving their profession permanently. And a lot of those self-reflection happened during the COVID pandemic, when everything turned upside down, when we stopped working from site, coming back and living in lockdowns. There are other aspects where that say that scientists are not necessarily that happy because there's a decline in research funding, and that Australian researchers have a low morale and a very strong job insecurity. And there's a lot of terms such as brain drain, where researchers are actually moving overseas or into other type of jobs. That one of the latest one in May 2022, as a great resignation hit academia. That's not only Australia, it's about academia in general in the world, but it really shows that there's some issues in science with a very strong wave of departures from early to mid-career scientists. So a strong mobility where people kind of think again, am I in the right career pathway? Or if I'm not, am I satisfied in my job position? Do I want to do something else? Do I need to change a different job? And that's what I wanted to talk about, that mobility. So there's 1 in 4 scientists that have been surveyed in 2021 that are on fixed-term contracts with an average contract length of less than 18 months. So there's a very strong job insecurity for early career researchers. And there's 4 or 5 early career researchers in Australia that have considered leaving science or their jobs in 2020, which is a very alarming statistic. So survey is illustrating job insecurity, workplace culture, mentoring, and sometimes questionable research practices that are impacting the job satisfaction and potentially compromising the science in Australia. So there are aspects of how to contribute and make these things better, and that's not the scope of today's presentation. Today is more looking at how a person feel and job satisfaction and changing position. And what I want to look at is that ikigai concept. What is job satisfaction? What does one person need in their life? Does it need to be in science or in something else? So ikigai is a Japanese concept, and when we kind of segment it into 2 different Japanese words, on the left we have iki, which is life or alive, and on the right-hand side we have gai, which is worth. So it really is about the worth of life, what the purpose of your life. And that consists of 4 different circles that when they are both here together gives you that ikigai. And I'm going to illustrate those 4 different circles now with you. The first one is to do what you love. And that's when you start in your career path, is generally where you get started, right? Is what interests you. So for me, went back a little bit into my old photos. What I really love is being outdoors. I used to love hiking, climbing, going in the snow, snorkeling. So there's quite a few photos from the past here. So I'm French originally, so I lived close to the Alps in Grenoble. So I used to go in the weekend for hikes. So this is one of those topographical map we used, because we didn't have smartphones in those days to kind of navigate around. Here it's me at the top of a cliff. So we did the long voie, I think it's called multiple pitch climbing in English. And so we used to climb and then go back down the cliff walking. So some very amazing experiences. Spent some weekends with my friends going hiking up through the mountain and then sleeping into some small houses like this one here. Yeah, that's me in Queensland going snorkeling when my family came. So I really loved being outdoor. Also loved traveling. So I have a few photos of traveling when I went to Madagascar. And this is a photo of Thailand in Bangkok. This is a photo of a small island near Madagascar called Mayotte. It's a beautiful place, landscape-wise. And this is here a photo of the Tinggi in North Madagascar. So traveling is definitely something that kind of filled who I am, what I love to do. But sometimes what you love get a little bit also shaped by what you've experienced as a kid. So as a kid, I used to go for walks or outdoor quite often. So there's a couple of photos on the top here of me as a kid with my brother, going for a hike in the forest or in the mountain near a lake. And in some way, I became a geologist because of my love of the outdoor, but also, I guess, part of it, my parents maybe have shaped me a little bit towards this direction. On the left-hand side is my mom. She's a ceramist, so she does a bit of raku. Here's a photo of her. Just cooked a culture and an enamel around it. And on the right-hand side, photo of my dad, young and nowadays, when he used to go into cave, look at rocks, and my dad's been collecting rocks as well as my granddad has been for a long time. So unfortunately, I know I've talked about geode hunting in that title. I couldn't find a geode hunting photo from my childhood, as most of my childhood photos are in France. And numerics was not on at those times, but part of it is definitely there in my memories, and I guess it shaped me from where I am today. Other photos and some of the aspects that I really enjoyed being outdoor and getting into that discipline of geology is to go into field trips. So these are a few photos of field trips. So that's one field trip we did when I was 5th year of university to go in Mount Viso. So Mount Viso is at the border between France and Italy. So I think it's actually in Italy. And it's at about 2.4 kilometers high. So the Mount Viso is much higher. It's above 3 kilometers high, but the plain where the refuge is about 2.5 kilometers. And there's an absolutely amazing view from up there. And there's some beautiful rocks, a lot of metamorphic grades we were looking at. So there's a few photos of field trips there. And then in 2006, I decided to get a bit more specialized in volcanology, geochemistry, and understanding igneous processes. So I went to Naples in south of Italy, and I lived there for 10 months. And I studied geology there as an exchange study. The ideal part is that I really could select all the courses, all the units I wanted to study. And of course, I managed to get to the top of the Vesuvius quite a few times. This is a photo of the streets in Naples. It's quite a very alive city if you haven't been there. Loved every single bit of it. Going to the Vesuvius, there's a field of scoria there. You see a bit of moss started growing on top of it. Here's a photo of a lava tunnel. So you have the lava flowing, and on the top of it is cooling, forming a bit of a crust. And then, of course, going into the field with my classmates and then looking at those, all those different layers of pyroclastic flows that came from several eruptions of surrounding volcanoes. So these are in the flagrant fields on the western side of Naples. A few photos of Vesuvius and Pompeii. There's also a photo here of Herculaneum and what happened during some of the previous eruption. There's of course some preservation of the people. So what they used to do that during the 79 eruption, the pyroclastic flow have preserved quite well some of the sculptures, but also there's from some gap by the decomposition of the bodies been a bit of a gap of air under the soil, and so they filled it with cement and they managed to recreate what was the position in which people have died, which was quite amazing. And that's a photo of the crater here of Vesuvius. Flagrant fields, that's on the western side of it. That's just a small video of the flagrant fields, and you can see it's quite active, and you have constant gas coming out, constant thermal coming out of the ground. You can touch the ground; it's quite hot. There's a camping at the edge of it. If you don't mind the sulfuric smell, my dad spent a couple of nights there. It's quite an amazing place. It doesn't feel like you're on Earth when you're in this place, actually. Another aspect of what I love is traveling, going outdoor and doing fieldwork in different countries. So here I went to South Africa doing my PhD to look at granitic rocks. So this photo of me here in the Greenstone Belt, south of Johannesburg, and there on the western coast of South Africa in Cape Town, looking at granitic rocks and their layering aspects in this area. Look at the micro XRF measurements and taking several measurements. This is a bit of a grid here to take up rock geochemistry. So that wasn't my study. I was just there more as an assistant and to visit. So just closing up that first cycle here of what you love, to then come to the second circle of the Ikigai concept, which is what you're good at. So lot less photo here of what you're good at, but a few things that I love to do. One that was my hobby is I love to sew. So I've been sewing handbags, clothes for my kids, and variety of things. And I guess another aspect of what I'm good at is I've always liked studying, especially studying earth sciences, physics, chemistry to some extent. I actually started with physics and chemistry at university because I saw that's what I enjoyed. And I had a small unit on geology, and I realized maybe at the end of it that I wasn't so interested about physics and chemistry, much more about geology. And then I moved completely into a geology, geoscience pathway. So got a few photos here of not necessarily what I'm good at, but reflection of what I have celebrated that makes me realize what I've been good at. Sometimes we don't realize what we're good at until we receive a trophy. But what do I receive a trophy? Oh yeah, because I have done that, and for doing this, I have got all those skills. One of the skills for me is determination and continuing until I get there. So I got a photo here of me celebrating with my classmates the end of my master. So we don't really have my ceremony in France. We generally do at the end of our presentation a bit of a lunch. And when I did my PhD in Brisbane, of course, I went to the ceremony. So this is here a photo of me with Scott Bryan, my PhD supervisor. And I was lucky enough to get my doctoral thesis award, so I had to go a second time to pick it up. So it was an interesting experience. So what you're good at really is those skills hiding behind those trophy and those ceremonies. And that might be, you might be good in swimming, or you might be good in problem solving, and those kind of aspects. And when you bring together what you're good at and what you love, then you have together a passion. Now, the third circle is what you can be paid for. And here I'm going to start talking a little bit about my career path and what happened after my master. So I've completed my master in 2008 in France. And then after that, I realized, I want a break. So that was my little detour in my last pathway. I came to Australia, I came to Perth, actually. I wanted to work in the mining industry and try that for a little bit. Unfortunately, I came during the economic downturn, and then I was hit, and I worked in a pizzeria shop. And then I struggled to figure out what I was going to do with my degree in geology. I wasn't sure where to continue after that, so I applied and applied and applied and applied. And you kind of wonder, am I going to stay in France, or am I staying in Australia, and what are my opportunities? And that's what brought me to look at the statistics here. So I've compared here France and Australia. It's approximative because it's job classified in a different way in different countries. But overall, there are about 6,000 employed geologists in France versus about 12,000 currently in Australia. And when you compare to the population, that'll make it about 2 in 10,000 people in France and 9 in 10,000 people in Australia. So the forecast is, of course, much better in Australia. I'll share here that the female share in those positions are quite low in Australia. It's about 25%. In France, it might be the same. I haven't managed to locate the statistics. The statistics are generally separated between industry and research, but they're not done by discipline. If you do know the statistics, let me know. And what are those different? What can you do as a geologist? In France, most of the research job is in hydrocarbons, in resources, or in research and consultancies. There's a little bit as well in public administration and other industries. In Australia, the majority is in mineral oil and gas industry, with a fair portion in minerals. There's also in research and consultancy 26%, and public administration and other industries with a bit of a lesser percentage than France. But really the focus is that in France, as a geologist, you might end up working either in water, geotechnical engineering, environment, and hydrocarbons. These are the main fields that are being focused on. In Australia, it's more minerals, oil, gas, resources. So after my master, I wasn't sure what to do. I mean, the only thing I knew I wanted to do was to come to Australia, take a gap year, try to work in the mining industry, and see if that suited me. So before going there, I needed to save money, and so I did a wide range of jobs. I did waitresses, but I also did a job that really meant a lot to me. Is I did a lot of science outreach activities. So I worked for Les Petits Débrouillards for a few months. So I did some. So this was actually, some of those photos here was actually doing my master's, doing my free time, when we did some activities with the kids during school holiday time, and we went into areas, underprivileged areas. I also did some exposition where I was taking all the exposition from schools to schools, and one was on Jules Verne, so it was on the thematic of the Earth and the from physics, chemistry, but also the geology side of it. And another one was on the human body. So a lot of fun time there. It wasn't just with kids, it was also with adults, with companies, with disabled people, so a wide range of activities. And then I went to Perth and I worked in a pizza shop for a bit, and I traveled and came back to France. And in France, I struggled and I applied for many, many positions, PhDs. Most of the time I didn't get an answer. Sometimes I did get an answer, which was negative. And in the meantime, I worked as a guiding tour on an open cut quarry, which is a Strombolian volcanoes that has been quarried to rebuild post-war. So the scories were being used for rebuilding houses. And I got really fit. I used to do about 10 kilometers walk a day, going around that volcanoes and showing there's about 2 different fields where the lava was coming from to deposit. And you can see also in areas where you have a series of deposits from different volcanoes of the surroundings, and looking at that, you can kind of open a book and try and looking at a map from which volcanoes those deposits are coming from. So very, very interesting problem-solving activities that we did with kids, and we had visits from large public schools, universities. So a wide range of activities we did there as well. Just so I put a few photos here of some of those different bombs and volcanoes that are shown on this pathway here. Okay. So really, what you can be paid for and what you're good at brings together the profession. So for me, my profession kind of started a little bit from my PhD, although you're just mostly on living allowances. And then I'll describe to you now a few of my research projects that I have done since I started as a PhD until today. So first I did my master's degree in France. Oh, so I actually started a little bit earlier. I did get paid a little bit for my master research. It wasn't much. So I'll present to you as well my master's research. So I worked on comatiite. So I did my project with Nick Hunt at the University of Grenoble. It's now called ISTER, but it used to be called a different name. And I worked on comatiite. So comatiite are magmas that have formed in the Archean, so about 2.7 billion years ago, so quite a while ago. And they're sometimes characterized by very interesting spinifex textures, and they're called spinifex because they look like a spinifex plant. And they're crystals that have crystallized in a certain way that create that textures. So I've worked on 2 comatitic flows that were really thick, about over 100 meters thick. One was located in Canada and was characterized by a very differentiated character in terms of composition and texture. So here we identify that character by magnesium content. So you see a very high magnesium content on the bottom part that is reflected by a cumulate layer of olivine. So imagine you have a thick flow coming in and ponding in a certain area, and it reaches about 100 meters. And you start crystallizing olivine crystals, and those olivines are going to settle to the bottom of the pile. And then the second mineral that crystallize a pyroxene, and they settle and create another pyroxene cumulate. And while it's crystallizing and settling crystals at the top of it, it's also cooling, and it's cooling so rapidly that we start crystallizing some spinifex type of textures of olivine and then pyroxene, and then in the middle, which is the last part to crystallize, we start forming a gabbroic type of texture. So here's a thin section photo, so a microscopic image, about 1 millimeter scale bar here of that olivine spinifex layer. The second flow that I studied was a very thick komatitic flow in West Australia, and very unusual because it had basically no differentiation, really strong high magnesium content of about 30% throughout. The textures, there's a few zones, but it's quite not quite as differentiated as the first one. And there were some interesting skeletal textures of olivines. These are olivine crystals are not single, crystals. They're really skeletal, really like kind of a fractal type of texture. And so I looked at the mechanisms that form those different textures. And the second part, we hypothesized that it was a higher volatile content that called the crystallization and the cooling of the flow to be instantaneous. And I won't go much more in details. The second aspect of my research when I moved to QUT to do my PhD was much more driven towards trying to understand where reservoirs for engineered geothermal system might be located in Queensland. So it was really driven by geothermal energy exploration at the time. So in Australia, there's not much more active volcanoes. So really is the power of geothermal energy really standing in those kind of systems, which call it hot dry rock or engineered geothermal systems. They basically consist of granitic reservoirs that is enriched in uranium, thorium, and potassium at about 3 to 5 kilometers depth. And then that reservoir is overlain by a thick sedimentary layer, generally characterized by a low thermal conductivity. That low thermal conductivity means that any heat produced by the granite due to radioactive decay of uranium, thorium, and potassium is trapped by that sedimentary layer. The idea was then to drill, circulate fluids to then pick up that electricity, that energy, and then to transform it into electricity, and then those fluids then recirculated into the system. There's been a lot of difficulty in terms of engineering, and the change of politics have kind of completely stopped now that view of geothermal energy exploration, but that was the aspect at the time. So on the right-hand side is a map that was generated by Geoscience Australia using temperature measurements at the bottom of the borehole that were extrapolated to 5 kilometers depth. And these were kind of mapped together to see areas where there were elevated geothermal gradients. And one big area that came up was this area here in Central Australia. And there's two known areas of geothermal energies. There's a Birdsville geothermal plant, which is generating electricity for the local population. And then there's Inaminka, where they've generated an engineered geothermal system in the early 2010s. So 2012, 2013, that was happening. And it's, I think, currently generating electricity to the local population. So I've done two aspects here for my PhD research. The first part was to try and understand what was causing these high geothermal gradients. So I sampled granitic rocks across the area from drill cores, and we studied them, characterized them. So we did mineralogy, geochemistry. We've done uranium lead dating of zircon to understand what they relate to, because everything is undercover in this area. Very little was known. The other aspect was to do some geothermal modeling to try and refine those temperature anomalies. So on the bottom part here is that temperature anomalies that I've shown you from the previous map. And the one in the middle is the one that I've refined using similar gradients. So we did new new heat flow estimates for about 160 drill holes in this area, and then extrapolated them, which gives a better resolution than that previous map. And you can see that it's still there, although it's a little bit more refined. Another aspect of my PhD was to compile geochemical and geochronological data of igneous rocks in Queensland. So I looked at data set from the surveys and also from independent researchers and brought them all together and tried to solve issues of duplicates. But then it allowed us to look at where the rocks were enriched in uranium, thorium, and potassium, which are here reflected by that heat production values. And we can see that they were elevated mostly in North Queensland, in the Mount Isa and the Georgetown Inlier, and a few aspects also along the eastern coast and also in northern part of New South Wales. And when we kind of segment those by also different associated igneous events, and we start seeing some, interesting history as to where these are located based on those terrains. And of course, I try to understand the processes that might have led those rocks to be enriched in uranium, thorium, and potassium. Which time frames they were from, where are they located, and are they from fractional crystallization? Is it source control? What was the magmatic process, or even a hydrothermal process, if there is any, that may have led to that enrichment? And the other aspect was also to look, and I'm not showing that here, but to look at where the sedimentary basins were on top and where potential targets could have been. And then the last portfolio of my PhD research, and again, looking at the processes, was to look at the role of crustal evolution, how repeated igneous activity in a certain part of the crust is going to affect the composition character of that crust over time. So really about that crustal maturation aspect. So we went to central eastern Queensland, so in inland of the Whitsundays, but also we did go to the Whitsundays and we sampled around all this area. And so here are a few photos of us going onto that little boat, flat tire, going on the field with a sledgehammer, and then collecting tons of rocks. So that was an interesting field trip, and then bringing together the data together, and we start looking at how the crust have evolved over time. So this area have experienced 6 to 7 different igneous activities. We got the early Carboniferous here, late Carboniferous, Permian in blue, Middle Triassic in red along the coast, and then we got the Middle Cretaceous, which are the Whitsundays, and the Tertiary as well. So there's multiple events in the same areas that as repeated is changing the character of the crust. And then we came up with a model on how the crust may have evolved, how repeated igneous activity is changing that character of the rocks that are later produced. And doing my PhD and my postdoc, I've also done a fair bit of dating on zircons, rutiles, but also other minerals like apatite and monazite. So that's one aspect of my research that I very much enjoyed, and when relevant, I'll sometimes bring in nowadays in some research project as well. After QUT, I moved to do a postdoc at CSIRO, and I kind of changed a little bit of discipline, still remaining in geology, of course, but then I moved into the world of fluid rock interaction, geochemical modeling. So what happens when you mix a fluid and a rock together, and can we try and predict mineral alteration zones that are associated with mineralization? So I focus mostly on sediment-hosted lead zinc deposits. So I've worked in trying to develop models to understand how organic matter might have an impact for generating lead zinc mineralization in sediment-hosted deposits, and also trying to develop an approach to model the fit of data. Model the fit between a model and the data. I'll come back to that image in a second. So one of the aspects of my research was really to look at how fluid circulate through a stratigraphic sequence, interact with them, and try to predict what will happen in the mineralogical assemblages as they circulate. And I won't have much time to go into details, but I'm happy to talk with some people if you are interested. But basically, some of the aspects of the modeling is trying to understand the speciation. So in certain systems, zinc is speciated as a chloride complex in high oxygen efficacy or very low pH. And what do we need to make them to precipitate? So if you look at the diagram here on the left-hand side, in blue, zinc being speciated in aqueous form, and in orange here it is speciated as it's a mineral basically. So there's two ways of precipitating here. We either have a loss of oxygen fugacity as a similar pH that causes the precipitation of sphalerite, or we could come from a rise of pH that causes the precipitation of sphalerite. And of course, depending on the deposit you're looking at, you might have different type of scenario. In that particular system, I was modeling that purple over here. And then the second project was to understand how we could rank geochemical models to empirical observation. Is there a way we can better do that rather than using the results of a geochemical model and then making a speculation out of it? So the idea here is we consider we have a unit of interest, we have a fault, and we have a fluid circulating in that rock. And over time, that fluid that is circulating over that rock is going to affect the chemistry and the mineralogy of the rock. So as you see here, each color is a different type of mineral, and as the fluid is coming into that rock, you can start seeing some zones of different mineralogical assemblages that are being generated. And we can then try and compare those to predictions. So this is a little star here on that model are different, observation, empirical observation. And so that's what we've tried to do. We've done about 300 to 400 models, and we've ranked them in terms of good fit based on the misfit between the empirical observation and the pathway. So to do that, we looked at the geochemistry of those observations. So if I go back to that previous maps that I say I will go back to, we're in Northern Australia here between the Macassar Basin and Mount Isa area, and we looked at the composition and they have suffered alteration. So we've tried to model that alteration aspect, and you can see that this it's not a very clear match, but we've done a range of models and a range of pathway, and then that misfit gets calculated. The main thing we kept constant in all those models are all the parameters except the fluid composition. And the reason to do that is then by looking at the models that has the best fit, we could try and unravel what was the brine composition that led to that lower misfit and therefore to that alteration. So you can see in red are the best models, and you can see the brine composition is a potassic rich or is in the intermediate area here. And then my current research activities is quite a range of projects, and I'm not going to go through them today, but just so I illustrate the variety of commodities. So I've been working on gold exploration project in the Eastern Goldfields, on critical metals in sediment-hosted deposits in Northern Australia, looking at the geochemistry and seeing which deposits might be more enriched in germanium, gallium, or indium, and what are the processes behind it. I've worked on nickel, and I'm still working on nickel exploration in mafic intrusion in West Australia, looking, so it's mostly magmatic processes there, so that these are mostly commercial projects. and tungsten molybdenum mineralization in North Queensland. And again, understanding the magmatic hydrothermal aspect and the processes behind the enrichment, but not also the processes, but also trying to unravel mineral alteration assemblages that are characteristics of those, and can we find some sort of footprint that can be used for exploration. Okay, I'll stop the science here because I can keep talking for hours on this. But basically, when we go back to our Ikigai circle, when we bring together what we love, what we're good at, and what we can be paid for, then we feel satisfied. But we're still missing that bit of impact. What we might feel maybe a bit useless, because what the world needs, what's my job contributing to the society. So what the world needs, and in my aspect, what the world needs for me is repurposing. So I like sewing. I've told you before. I think I'm okay. I'm quite good at it, and so I like to be able to take my old jeans or my partner's jeans and put them into handbag, or get my scraps of sewing and then stitch them together and make a new fabric out of it. It's probably a small footprint because it's just something I do as a hobby. But in terms of my job, what I like to do is going into an area of research that is going towards a more towards building a better world. So I go into critical metals. And I'm sure many of you have heard about critical metals before, but if you haven't, critical metals are metals that are considered essential for the development of new technologies or sustaining other technologies. And these might be some elements that are in areas where the supply is dominated by one country. So rare earth elements is one of those critical metals, and these are quite well known to be associated in our everyday use device like a smartphone. So we have rare earth elements in the screen, in the electronics. We have lithium in the battery. We have indium in the touchscreen. So there's a range of critical metals. Here, there's also other metals that are not critical that are being used in the smartphone. Just to show you that the technologies that we're using are full of those metals. And while we try and recycle, most of those metals are not necessarily yet have the technology to be recycled. So this is, to me, what I identified as my impact, as my vision. And I dare you to think as well as what that might be for you. Now, when we bring together that what the world needs and what we can be paid for, then we have a vocation. And when we bring together what we love and what the world needs, then we have a mission. And if we bring all three together, well, we feel happy. We feel like we have a sense of purpose. We have a vision. We do what we love. We're being paid for. But if you're doing something and you're missing the what you're good at circle, then you might feel a bit frustrated and a bit challenged because you might not have all the skills you need to do that. And you might feel a bit stretched, and some people might actually give up that opportunity to be in that circle. When you have the top three circle, but you're not being paid for, then, well, you don't really have a wealth, and sometimes people can continue in that pathway. And when you're missing the top circle and you just have what you're good at, what you can be paid for, and what you need, well, you might feel a bit sad, a bit empty, because you don't do actually something that you love. But when you bring those four circles together, that's when you have your ikigai. That's when you have your sense of purpose for life. You're happy. You're using your talents for an impact, for a vision that you have, and you as well can be paid for, and you can sustain it. And so, to me, my ikigai is to unlock the secrets hidden in work, in the hope to build a better world. And I'll leave it here. Thank you.